Hi, everybody. I'm going to go over the Pendulum Clock Lab, the first day, the page 1 and 2, as well as how to complete page 3 of the lab. So the first off, we talked about these first two questions together. The first question is, what are some examples of a pendulum? We came up with a child swing. We also, many of you came up with wrecking ball. I am drawing a blank on some of the other ones, but some good ideas. Number 2 is was just really a guess. So we weren't really expected to know that. Just to give an idea of what you think might affect it. And then we have the warm-up portion. So we use the simulation to find the period of the pendulum in the default settings that the Gizmos starts with. And we determined that this period was about 2.8 seconds and that it is running too slow because one swing to the right should take 1 second and then swinging back should take 1 second. Because every time the pendulum swings, the second hand ticks forward 1. So it's registering on the clock 1 second, but it's taking 1.4 seconds. So every back and forth swing should be 2 seconds because 2 seconds are recorded on the clock face, but it takes 2.8 seconds. This means that the clock will be behind. If it continues to run like that, it will become behind the time. It'll be running too slow. Then your first experiment was to determine the effective length of the length of a pendulum upon its period. And a sentence frame for that hypothesis is if the length of the pendulum, and you can say increases or decreases here, then the period will increase or decrease. So what do you think the effect will be? If I increase the length of the pendulum, will the period increase or decrease? So literally just pick one of those and then predict what you think will happen to the period. So this is what the data table should look like for your first experiment. The angle will remain 25 for all, the mass 2 for all. And our first one I just pulled from the default settings of the clock that we did at the beginning. So 200 centimeters length, 2.8 seconds. Then you're going to collect the rest of the data, and I'm going to demonstrate that really quickly here. So here are the original settings. You have a 2 kilogram mass indicated by the 2. You have a starting angle of 25 degrees as indicated here. So right here gives you the starting angle. It also gives you the length in centimeters. Note that the number on the bobs indicates the mass in kilograms. We are on Earth, which means gravity is 10 meters per second squared. And we're going to record the time between swings. So to do that, I'm going to start clicking mark time every time the pendulum swings to the left. So left, mark, left, mark, left, mark. So every time it swings left, I'm going to hit the mark to record that interval. Now remember, this is the original settings. This is also the settings that it had when we found that it was 2.8 seconds and determined that the clock was running slow. So I don't know if you notice this, but if you look up here at the top, this is the actual time. I'm filming this on Wednesday night at 8:10, and my pendulum clock is reading 8:10, but it is several seconds behind the actual time. So this is evidence that proves that we were right the one in the first page when we said that it was running too slow. Because if with the default settings, the seconds are not going fast enough. Like they're not actual seconds. They're taking longer than a second. So the longer this runs, the more behind the clock will become. Now here's a little trick for figuring out the average. So if you hit export on here, it'll download an Excel document or a numbers document, depending on the computer you're using. And what's a really cool trick if you're using an Apple computer is when you open the Numbers app, it gives you the list of numbers. And what you can do is just highlight those And then down here at the very bottom, it has the sum and the average, the min and the max. So the average is 2.85, which remember we estimated before that it was about 2.8, right? So we estimated that it was about 2.8, which is almost exactly what we got in the experiment as well. Okay, so 2.8 seconds was our original estimate. This is supposed to say too slow. Okay, hypothesis. So that came over from this one. Okay, and copy. Okay, so that's our first measurement. And you can put 2.85 if you want. It's going to round out eventually, but 2.85 if you feel like it. Then I'm going to go ahead and pick a couple more lengths to do. So let's say 180, 160, 140, and 120. You can pick your own, but that's what I'm going to just use for this example. So back to the clock. I'm going to go ahead and clear this. Oh, new things I didn't know I had. Okay. So let's reset that. And we're going to change the length to 180. So you click on the bob and push it up till you get to your number, 180. Play. Okay. I'm going to export my numbers. Okay, average 2.7. Okay. Okay. Average 2.5. 2.5. Okay. Now, for the purposes of this first experiment, do continue with the 140, 120, or whatever measurements you chose. For you can see, I think already there's a trend though. So as I decrease the length of the pendulum, I'm actually decreasing the period as well. So those are directly related. So if the length of the pendulum increases, then I would say the period increases. If I said the pendulum length decreases, then the period would decrease. What did you discover? The length and period are directly related. Okay. Was your hypothesis correct? So this is yes or no, depending on what you put originally. All right, extend your thinking. Measure the pendulum period for the following pairs of lengths, 50 and 200, 60 and 240. So we already have the 200 of 285, 2.85. I'm just going to do 2.8 here because most of our numbers are going to be only one decimal place. And then for 50, we would run that test again. So pause, reset, drop it to 50 centimeters. Wow, that's really short. Okay, I don't even know if I can see that. Okay, so I'm not going to do the expert thing for this one. It looks like the average here is 1.4. So I'm just going to use that 1.4. And I'm not going to actually do this one, but I will put the numbers that you should get, 1.6 and then 3.1 or 3.2 approximately. Okay, so then we have to identify the relationship. It says compare these two and then compare these two, 50 to 200. To do some quick algebra here, 50 times what equals 200. To solve for our unknown, you would divide 200 by 50. So 200 divided by 50 is 4. 240 divided by 60 is 4. So 60 times 4 would be 240. Then you do the same thing for the pendulum period. So the pendulum period is 1.4 for 50 centimeters times what equals 2.8. And so you would do 2.8 divided by 1.4, which would be times 2. So the answer here is 4 and 2. If I multiply the length by 4 of the pendulum, 50 times 4 is 200, then I double the period. So I would multiply it by 2. So if I knew the period and the length and I needed to double it, I would need to quadruple the length and that would double my period. If I needed to split it in half, I would do the opposite. All right, so I'm going to stop right there. That was day 1.